In this recording, we'll talk about the electrical field. If you recall, when you dealt with gravity, we say, for example, that an object at the surface of the Earth is going to have a weight that's equal to m times g. Okay, that's the gravitational force that the Earth exerts on that object. Now, m is the mass of the object. What's g? G is a measure of the gravitational field at that location. You all were aware then, if we move further away from the surface of the Earth, we are going to have to use a different G. The same thing applies in electricity. If we have a certain charge, like this positive charge here, around it we are going to have what we call an electrical field. That's due to that charge. That electrical field, once we know it, we can find the electrical force acting on any other charge by using an expression similar to this one. We'll get to that in a little bit, but for now, the expression for electrical field, and we use E for electrical field, is given by this. It's K Q over R squared. K was the same constant that we used for the Coulomb's law, 9 10 to the 9 newtons meter squared per Coulomb squared. Q is the charge, and R squared is how far are we from the charge. Notice here it's very much similar to the equation for the force. However, we have only one charge. For the electrical field, we need only one charge. It's the electrical field due to that charge, and R is the distance from that charge. Its again is a vector, and we are using the magnitude here for the equation. Now, what about the direction? For the direction, a positive charge is going to result in an electrical field pointing away from it. A negative charge is going to result in an electrical field pointed towards it. And we'll deal with that later on. There is the concept of a test charge here. A test charge is a tiny charge that you can place somewhere to see what kind of field you have in a particular location without affecting the actual field. Think of it like putting a mass at the surface of the Earth. It does not affect the gravitational field due to the Earth that much, like most of the tiny masses at the surface of the Earth. However, if you are going to take a large mass like the Moon and put it close to the Earth, that's going to have a much bigger effect, and that would not be a test particle. Now, as I mentioned a minute ago, so throughout the universe, due to any charge, we are going to have an electrical field, and the direction of that electrical field for a positive charge is going to be pointing away. For a negative charge, is going to be pointing towards that negative charge. Now, the strength of that electrical field is going to diminish the further away we get away from that charge. Remember, it has that 1 over R squared dependence. Now, when we have lots of charges, like in these cases here, the overall electrical field is going to be the combination of the electrical fields due to the different charges. Remember, they are vectors, and we have to add them up. Like in this case here, we have a positive and a negative charge. If we come to a point like here, the electrical field due to that charge is going to point this way. The electrical field due to this charge is going to point this way. So the overall electrical field is going to be something in an intermediate direction, and the magnitude, you can find it using addition of vectors. Same case, if I have more charges here, one interesting thing here, one exercise that you can give yourself is trying to figure out which charges are positive and which charges are negative. Notice, like in a point like here, the electrical fields from the various charges somewhat seem to cancel out, where we essentially have no electrical field. But notice here, due to charge 1, it is gone out, so it must be positive. Charge 4, the electrical field is pointing in, so it must be negative. Positive for 2 and negative for 3. Now, quite often, instead of just drawing the electrical field, we draw what we call electrical field lines. The electrical field lines would be lines originating at the charge And for a positive charge, they're going to radiate outwards, like what you see here. For a negative charge, they're going to radiate inwards, like you see here. And here we have some tiny test charges. Now, the test charge in both cases here is positive. So if I place a positive charge here, the positive charge is going to experience a force, a repulsive force, in the same direction as the electrical field lines. And then if I have a positive charge in a region where the field lines are pointing towards the charge, now the electrical force acting on that charge is going to point towards the charge. But notice here, if I have a positive test charge, in both cases the force is pointing in the direction of the electrical field. And here both of them are pointing towards the charge. Here both of them are pointing away from the charge. Now this is the electrical field representation, so it's showing us the electrical field vectors at every point, and essentially the colors are somewhat represented for us the strength of the electrical field. However, here we are drawing electrical field lines, and you notice here they are coming out of the positive charge and into the negative charge. This probably should remind you of magnetic field lines that you might have seen in an earlier course when we talked about magnetism. One thing interesting when you look at electrical field lines, the more lines you have close to each other, that's a representative of the strength of the electrical field. So we have a strong electrical field here, strong electrical field here. It weakens here because we have the lines are not as concentrated anymore. Now, what if I have, we notice here we looked at a positive and a negative charge, and this is what we got. What if we have two negative charges or two positive charges? What's going to happen? Okay, and remember, they are going to, the negative charges here, so it's going to go in, but in the middle, in a point in between, what's going to happen? The electrical field due to this is going to be like this. The electrical field due to this is going to be like this. So they're going to cancel out. Now here, the electrical field due to this one is going to be like this. The electrical field due to this one is going to be like this. They're going to again cancel out. So you get something like this. See, if we have positive charges in the middle, we have no electrical field. In the middle, we have no electrical field. And that's, here they're going out and they add up in all places as vectors. And you see the same look here except for the orientation of the electrical field. Now, if we draw it in terms of field lines, it's the same thing. So in the middle, they cancel out, and then you have that kind of pattern that looks very similar between the two cases. What if we have charges that are unequal? If they are unequal, of course, they are going to cancel out, not halfway between them, but somewhere else. And you see something similar to here. And you see closer to the stronger charge, I have a bigger concentration of electrical field lines. So these are more concentrated than here. For the same area, we have more electrical field lines. Okay, that's another case of unequal charges, but that are opposite. So you see here in this case, we have zero electrical field here, zero electrical field lines here, strong electrical field here, and so on.